Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Slip Line Method, and it is going to introduce the mathematical derivations. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the equilibrium and yield conditions. Now we consider footing under increasing load. Impending plastic flow of the soil occurs when a sufficiently large region of the soil beneath the footing is stressed to its limiting or yield condition, resulting in an unrestricted plastic flow of the soil beneath the footing. At the instant of impending plastic flow, both equilibrium and yield conditions are satisfied in the region near the footing. For soils, the Coulomb criterion is widely used for this yield condition. Combining the Coulomb criterion with the equations of equilibrium gives a set of differential equations of plastic equilibrium in this region. Together with the stress boundary conditions, this set of differential equations can be used to investigate the stresses in the soil beneath the footing at the instant of impending plastic flow. In order to solve specific problems, it is convenient to transform this set of equations to curvilinear coordinates whose directions at every point in this yielded region coincide with the directions of failure or slip line. These slip directions are known as slip lines, and the network is called the slip line field. In this video, we will study the mathematical derivations of the slip line method. For the sake of simplicity, the soil is assumed as an ideally granular medium. The shearing resistance of the soil is phi. We start with equations of limiting plane equilibrium of a wedge. The properties of an ideally granular medium make it possible to obtain solutions to many problems more easily if we consider the limiting equilibrium of a wedge. It will be shown that the solutions to all these problems can be obtained in closed form. We shall start by making a detailed study of the equations of limiting plane equilibrium, using for the most part a system of polar coordinates r theta. We shall confine our attention to the case when the self-weight acts in a direction parallel to the y-axis. The differential equations of equilibrium are shown here, where gamma is the self-weight of the soil. According to the Coulomb yield criterion, and assume the soil is cohesionless, then the condition of limiting equilibrium is shown here. Now we shall introduce a rectilinear system of coordinates xy and denote the angle between the direction of major principal stress and the x-axis by y-phi, and the angles of inclination of the slip lines relative to the x-axis by y-phi minus or plus epsilon. The negative and positive sign means the characteristic directions. The direction of the plane on which the shear stress is positive is termed the alpha characteristic, and the direction of the plane on which the shear stress is negative is termed the beta characteristic. It is of particular importance to investigate the slip lines, which consist of two characteristics intersecting each other at the angle 2 times epsilon equal to 90 degrees minus phi. We shall represent the stress components sigma x, sigma y, and tau xy in terms of sigma and phi in these equations. We turn now a system of polar coordinates r theta, which it is sometimes more convenient to use, and we shall denote the angle between the direction of major principal stress and the straight line OD by psi, and the inclinations of the slip lines relative to the same line OD by psi minus or plus epsilon. We shall represent the stress components sigma r, sigma theta, and the tau r theta in terms of sigma and phi in these equations. In this case, y-phi is the angle between the direction of the major principal stress and the x-axis, and psi equal to y-phi minus theta between the direction of the major principal stress and the line OD. Many problems on the equilibrium of a wedge of an ideally granular medium possessing self-weight can be studied on the assumption that all the stress components sigma r, sigma theta, and tau r theta are proportional to r, or that sigma is proportional to r, and var phi and psi depend only on theta. Therefore, we will assume that var phi is a function with theta, psi is a function with theta, and we shall introduce a new function chi, defined by the equality sigma equal to gamma times r times chi. Substituting expressions of the stress components sigma r, sigma theta, and tau r theta, which satisfy the condition of the Coulomb yield criterion, into the previous differential equations of equilibrium and rearranging, we obtain a new set of equations. This can be solved for the derivatives, so that we obtain the ordinary differential equations. These slip lines are inclined to the x-axis at angles var phi minus or plus epsilon, and to the line OD at angles psi minus or plus epsilon. Therefore, the differential equations of the slip lines are shown here. Next, we will learn the boundary conditions of foundation problems. Let us now consider the limiting equilibrium of a medium bounded by the x-axis, which is free from pressure and inclined to the horizontal at an angle delta. The stress state set up in the body will be called a simple stress state. We shall consider the equations which define the limiting plane equilibrium of a granular medium, using an ordinary system of rectangular coordinates x, y, and considering, for generality, that the x-axis is inclined to the horizontal at an angle delta. The basic equations are the differential equations of plane equilibrium, which contain the density of the soil gamma. Then it is independent of x and is defined by the differential equations as shown here. They can be integrated to give these equations. Thus, the stress on inclined straight lines parallel to the x-axis acts in a vertical direction, P equal to gamma times r times sine theta. The state of plane stress at some point capital P can be conveniently represented by a Mohr circle diagram as shown in this figure. The angle lambda can be expressed without difficulty in terms of delta. According to the sine rule, the equations of lambda and sigma are given by these expressions, where kappa is equal to negative or positive 1 for two characteristics, and sine capital delta equal to sine delta over sine phi. In the particular case, when delta equal to 0, we have the new expressions of lambda and sigma. To interpret the two characteristics, there exist two different stress states. For given values of P and delta, one of them corresponds to kappa equal to negative 1, so that the lambda and sigma are expressed here. The other corresponds to kappa equal to positive 1, so that the lambda and sigma are expressed here. Now we know the stress state in the soil body. Next, we can introduce the stability of foundations. We shall study the limiting equilibrium of a wedge when one side is free from pressure and the other, which is horizontal, is subject to a pressure P acting at a constant angle delta to the normal. It is convenient to try to find this pressure in the usual form P equal to gamma times R times PO. We shall investigate the region of limiting equilibrium AOOA, in which a simple stress state exists, and the adjacent limiting region AOB. These regions are divided by a straight line, a slip line, theta equal to epsilon passing through the point O and denoted by OA. In the region AOOA, with kappa equal to positive 1, we have these equations. On the straight line OA, we can input these boundary conditions. On the straight line OB, with kappa equal to negative 1, we take these boundary conditions. In the region AOB, we must find the solution to the previous differential equations of equilibrium, which satisfies the boundary conditions on the straight lines OA and OB. Now we will make examples to explain the application of the strip line method. We give solutions to the strip foundation problems for an angle of internal friction phi equal to 30 degrees, which is based on the numerical integration of the differential equations of equilibrium by the method of finite differences. In order to solve the ordinary differential equations, we have to know the initial value PO. When delta equal to 0, PO is 15.3. When delta equal to 30 degrees, in the calculation, delta is negative 30 degrees. PO is 29.6. This slide shows the strip lines of smooth footing and rough footing. The blue curves are alpha characteristic. The red curves are beta characteristic. Now we can try to use the current method to calculate the bearing capacity factor N gamma. This table enumerates the N gamma footing pressures for the three cases, delta over phi equal to 0, 0.5, and 1. It also compares the current values of N gamma with current recommendations in Eurocode 7. This equation overestimates N gamma by up to 40%, or returns values of N gamma equivalent to angles of shearing resistance phi up to 2 degrees higher. An empirical search for a better fit using a similar form of equations indicates that these are more suitable formulation. Predictions using this equation are given in the table. These give results within 1% of the current theory over the range phi from 20 to 50 degrees. The error increases to a 3% underestimate at phi equal to 15 and 55 degrees. It is clear that the current method has an excellent agreement with the empirical formulation. From conclusions, what we learned? In a strip line solution, only a part of the soil mass near a structure is assumed to be in the state of plastic equilibrium. The solution consists of constructing a strip line field in the region, which satisfies all the stress boundary conditions that directly concern the region, as well as the equilibrium and yield conditions at every point inside the region. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I'm happy to answer any questions. Thanks for your watching.